Okay guys, welcome to today's lesson in statics. Today we'll be covering problem 51 from chapter 3. So number 51 says, a small boat hangs on from two davits, one which is shown in the figure. It is known that the moment about the z-axis of the resultant force Ra, exerted on the davit at A, must not exceed 279 foot-pounds, an absolute value. Determine the largest allowable tension in the line ABAD when x equals 6 feet. So as you can see, I've gone ahead and written down what we know. We know the dimension x in the figure is equal to 6 feet. And we know the moment, maximum moment on the z-axis, is 279 foot-pounds. Good. So now let's see what we need to find the moment about axis z. So we have mz, a scalar value, will be equal to the k-hat product, this is on the z-axis, of the moment around the origin of the moment at point C in this case. Now the moment about point C we find by doing the cross product. So we'll write this down. Moment about C is equal to the cross product of the vector going from point C to point A, which would be position vector R, C to A, cross with, they told us the resultant force R at point A. So once we find out the position vector from R from C to A, we can then find out the resultant at A due to the forces acting on point A at the davit. We can then compute what the moment about the origin is, moment about C is, and then use the mixed triple product with the K vector for moment about Z to find out what this value is for the tension. Good. So let's go ahead and find the position vector from R from C to A. Go ahead and write that right here, R from C to A. Looking at the figure, going from point C to point A, we're going 0 feet in the x-axis, because we're in the same plane, we're in the YZ plane, so it'd be 0 I hat. We're going up a distance that looks like a 7.75 feet in the j hat direction. And finally, looks like we're going a distance of 3 feet out along the z-axis, coming out of the page. So plus 3 in the k-hat direction. So we have RCA already found. Good to know. Now we need to figure out the resultant at point A. So let's draw a freeway diagram. We can see in the figure, looking at point A, we have a tension force pulling down, and then a pulley, which has a tension force pulling down to point B again, and then a tension force going to point D. So let's draw a freeway diagram for point A. At point A we have, looks like two tension forces going from TA to point B, tension going from point A to point B. We have two of these vectors. And then we have a tension going from point A to point D as well. So we have a tension going from A to D. So our resultant then at point A, our resultant force, this vector would be equal to 2 times the tension TA to B vector plus 1 tension vector going from A to point D. Good. Now we're going to figure out what the tension going from A to B is first. So looking at the diagram, notice our first diagram we have a force pulling down, two forces pulling down. They're going down in the negative y-axis direction or the negative j-hat direction. So if I were to write this out, I'll write out my tension vector going from A to B is equal to tension in the line AB, AD, the whole line, times negative j hat. So negative j direction, negative y-axis direction. So that's my tension going from A to B. It's negative tension in the line ABAD in the j hat direction. Good to know. So we have now tension AB. Now all we need to do is to determine what tension A to D is. So we need to figure out first what the position vector going from A to D is. So tension vector A to D will be determined by finding out what the position vector going from A to D is first. So look at the diagram again. Going from point A down to point D, looks like we're coming out x feet in the I hat direction, which is we're told is 6 feet, so it'd be 6 in the positive I hat direction, in the positive x-axis direction. Now we're going down 7.75 feet, so we're going down negative 7.75 feet in the j hat direction. And finally, we're going into the page on the z-axis and the negative z-axis by 3 feet, so we have minus 3 in the k hat direction. Good. Now we need to figure out what the distance is from A to D. So we figure that out by doing the magnitude formula, which is the distance formula, where we simply square each component, add them together, and take the square root. So we have 6 squared plus, in parentheses, the negative values, 7.75 squared plus, in parentheses, again, negative 3 squared. So going to our calculator app, we would have 6 squared plus, in parentheses, negative 7.75 squared plus, again, in parentheses, negative 3 squared. We'll take the square root of this number, and we get 10.25 as our distance from point A to point D. Now we can determine what the value of the tension vector AD is. So tension AD would simply be, well, tension of the line unknown, AB, AD, divided by the distance value, A to D, and then multiplied by the position vector, A to D. So times vector AD, or position. So if we were to substitute this value in, we would have tension in the line AB, AD, and then we're going to divide each one of the components by the 10.25. So we have this divided by 10.25 times our position vector, which is 6 I hat minus 7.75 j hat plus minus 3 in the z-axis direction, minus 3 k hat. So now we're going to divide each one of these values by the 10.25 distance. So our tension vector, write this right here, our tension vector AD is equal to tension AB AD times 6 divided by 10.25 in the I hat direction, the x-axis, so 0.585 I hat minus 7.75 divided by 10.25, which would be tension AB AD times 0.756 in the j hat direction minus 3 divided by 10.25 in the k hat direction, so 0.293, so minus 0.293, and then times tension AB AD in the k hat direction. Good. So now we have our tension value AD, we have tension AB, we can figure out what the resultant is of those two forces, RA, at point A. So resultant RA, which we know is equal to 2 tension AB plus tension AD, would be 2 multiplied by our tension AB, we determined was simply the tension of the line ABAD times the negative j hat direction. So it's 2 times negative tension ABAD in the j hat direction plus now our vector tension AD. So we have all these components. So we're going to, the I hat component will not be affected, k hat will not be affected. We'll only have to, simply have to combine the two j hat components. So we're going to write this out again real quickly. Plus 0.585 tension ABAD I hat minus 0.756 tension AB, AD in the j hat direction, and then minus 0.293 tension AB, AD in the k hat direction. So now we can finally combine these two vectors, our j hat vector here and here. So we'd have negative 2 minus 0.756. This would give us a value of negative 2.756 tension AB, AD in the j hat direction. Our other two components will be the same. So resultant at A, I hat and k are not affected. This is only a j hat and j hat components added together. So this would be equal to 0.585 tension AB, AD, and then minus 0.293 tension AB, AD in the k hat. Now we have a resultant at A. We can do the mixed triple product up here as we originally talked about and determine what the z-axis component is. So we're dotting k hat by these two. So what that would look like, we write this out as moment about z is equal to k hat dotted with the cross product position vector from C, the origin, to point A where the force is being applied, creating the moment. So cross the resultant A. So what this would look like would be our typical determinant matrix, but the k hat dotted with these two cross products means we'd have 0 for the I hat, 0 for the j hat, and only a k hat component up here for our top row for our determinant. Good. Now we have our position vector RCA has 0, a 7.75 in the j hat, and a 3 in the k hat. Now our resultant vector A, go ahead and move this up a little bit. Our resultant vector A has all three components. So we would have a 0.585 tension, just write T for tension. We'd have a negative 2.756 T for tension, and then a negative 0.293 T for tension. Good. Might spread these out a little bit. 3 and our k hat dot. Then we're going to copy again the I hat and j hat components. So we'd have 0, 0, 0.585 times tension value, then a 0, 7.75, and a negative 2.756 T for tension. Now, to solve this determinant, we're going to have to do our multiplication going down to the right adding, up and to the right subtracting. So I'm going to do my down to the right one time here. That would give me a 0. Going to do my down to the right again. That would give me another 0 product. Do my down to the right again, have another 0 product. So all the top row, or all the adding rows are 0. We do have a k component here. We're subtracting now. In parentheses, it would be 7.75 times the 0.585 and the tension for line AB, AD. Then we'd have a 0 value again, minus 0 again, and a minus 0 again. So all these terms will be 0. This is our moment z, which we know is effectively equal to 279, as we were originally given the problem, 279 foot-pounds. So we'd have 279 is equal to, we're going to multiply these two coefficients together, 7.75 times our 0.585, and we get negative, there's a minus sign here, 4.534 times tension AB, AD. We were told this moment value is an absolute value, so we disregard the sign. The sign's unimportant. It just tells us which direction the moment was originally pointing in. So we divide this in absolute value. It would tell us that tension ABAD, if we divide them by the 4.534, again, this absolute value tells us we can ignore this negative sign, divide by the 4.534. This tells us that tension ABAD, if we divide this 279 by 4.534 gives us a tension value equal to 61.5 or 61.5 pounds of force. So here's our answer for our tension value, number 51, chapter 3, 61.5 pounds of force. Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.